So today we're going to continue learning more about logarithms today. We're going to cover something called the law of logarithms. This is kind of like the exponent laws that you would have learned back in Math 9, but let's get going. So first things first, we're going to cover some methods used to simplify and solve logarithmic expressions today called the laws of logarithms. We'll start with a quick recap of logarithms. I know when this video, of course, when you'll be watching it, you'll already have had a long weekend, so I thought, you know what, maybe we should just go over this first. Then we'll talk about calculating logarithms, especially ones without a base of 10. Then we'll learn about those laws of logarithms I was mentioning. Then we'll do a ton of examples today. Like there's going to be a metric ton of examples we're going to have to go through. And then, of course, I'll give you guys some practice time. Here we go. So just a quick recap of logarithms. Remember that a logarithm is just the inverse relation of an exponential function. So it's just kind of like you've switched everything all around. So we're going to start by writing log base 4 of x equals 3 as an exponential function and then solving it. Well, here's how I always go about doing it. I start by looking at the base. Regardless of whether I was given a log or whether I was given an exponential function, the base is where you should start. So I'm going to start by taking this base of 4, and I'm going to say that's going to be the new base of my exponential function. So we're going to have a base of 4. Now, the exponent, when you're going from a logarithm to an exponential function, the exponent is what the logarithm was equal to. So we're going to say 4 to the power of 3 is equal to whatever was inside the log in the first place, so x. It's kind of this big switcheroo. And again, if you always start with your base, it usually becomes a little bit easier to start getting in the motions of it. You know, you start with your base and your exponent's the answer, and then the thing in the log comes out, right? So it's this big workaround. Now that we have this, we can actually quite simply solve this. This is just 4 to the power of 3 equals x. So in other words, 4 times 4 times 4 equals x. Well, I know 4 times 4 is 16, and then 16 times 4 is 64. So I can say that x is going to equal 64. Now, the whole point of this, of course, is when you look at this in a logarithmic expression, it's not clear what x is. But as soon as you turn it to an exponential function, it becomes more clear what x is. Both of these forms, whether it's an exponential function or a logarithm, both of these forms can be used in tandem with one another to figure out some solutions to problems that you have. So sometimes you might not be able to find what the value of x would be in an exponential function, but as soon as you turn it to a logarithm, you can. Now, that actually brings us into a little bit of an issue that we can sometimes encounter. Up to this point, we haven't been able to solve logarithms like log base 3 of 18 equals x. And the reason for this is if you saw this, you go, okay, well, we just have to turn it into an exponential function because you can't plug in log base 3 of 18 in your calculator directly. But then you find it'd be 3 to the power of x is equal to 18. But 3 to the power of nothing gives you 18, at least no whole number. So you wouldn't be able to solve for x that way. Now, to solve these, we actually have to use an identity that allows us to change the base of a logarithm. Okay, so in other words, when you have a base of 3 or something, you're going to need to use this identity because you can't directly put a base of 3 in your calculator. If you have a TI-84, you might be able to actually, like I'm kind of going to eat my words on that. But again, I'm not used to a TI-84. I don't know where you'd access that. But no matter what kind of calculator you have, as long as it has a logarithm button on it, you can use this identity to solve it. Now, let me kind of explain what this means. Before I explain this, let me just remind you that in your calculator, your log button, so if you tried like log of 100, for instance, that log button in your calculator is really doing a log of base 10, and I was kind of mentioning that down here. So really what your calculator would be doing is log base 10 of 100. So in other words, 10 to the power of something equals 100, and then of course we know that that something would be 2, because 10 to the power of 2 is equal to 100. However, like I was mentioning, your calculator can't put a base that isn't equal to 10 into it directly. What this identity does is it says, okay, you have a log of a base b, whatever b is, of some number c. To calculate this, you can set this equal to log of a different base a of c, so what was in the log in the first place, divided by log of that new base a, the same as what you had on the numerator up here, of your old base b, right? So this old base becomes the insert of the logarithm on the denominator of this identity. Now, the value of a can be literally any other number. You could say if this was like log base 3 of c, you could change this to log base 2 of c over log base 2 of 3, right? It really doesn't matter what that is, right? So in other words, you can change a to any other number. Now, generally, of course, to be able to calculate this on our calculator, I know I'm kind of rambling with this, but generally, you might as well just say that a is equal to 10 every single time, right? That's what this identity is used for. Literally 99% of the time is just to say, you know what, we're going to change it so it's log base 10 of c divided by log base 10 of b, because then you can throw it in your calculator directly. Let me show you what I mean, okay? I know that was kind of a long ramble here. Showing you what I mean, let's say we're going to solve that log base 3 of 18. Again, we can't do it using an exponential, so we have to just like tackle it using logs. Well, from this identity up here, we can say b is like our 3 and c is our 18. So we could set this equal to log base 10 of 18 divided by log base 10 of 3. Now again, I'm just writing the base 10 just because that's good habit, but if you just wrote log 18 over log 3, that means the same thing, because when you don't write a base on a log, you just assume that the base is 10. This is something you can throw into your calculator. If you go onto your calculator and again, the log button's right next to the 7, if you have a graphing calculator, of course, just go log 18 divided by log 3, and you're going to get a decimal. I'll just round it to the nearest hundredth. This is going to be 2.63. So as we suspected, of course, it can't be a whole number because there's not a whole number power that's going to turn 3 into 18, because 3 to the power of 3, for instance, is 27. So we have to have something in between. So 2.63 is a pretty good approximation. All right, let's do some more questions on this. Evaluate the following logarithms. First one, log base 7 of 343. Now, if you really know your powers of 7, you're probably like scratching your head as to why we're doing this on this one, because it actually is going to be a whole number. 7 to the power of something does equal 343. But changing this into an exponential, like saying 7 to the power of x is 343, this still becomes a game of guess and check. You still have to go, okay, what x is that going to be? And you have to throw some numbers in there. In other words, you're still just calculating it by throwing numbers into it until it works. We can do it better than that. Using that identity that I just showed you, we can say that this is actually equal to log of 343 divided by log 7. And of course, the log without a base that I'm referring to is log base 10. I'm just saying how your calculator is going to put this in. So anyway, if you throw this in your calculator, I don't know why I'm doing this because I know what the answer is, but log 343 divided by log 7 is equal to 3, right? So just check and just make sure making sure it just still works. You know, you're just hoping like the rules of math didn't change overnight or something. But anyway, yeah, so log 343 divided by log 7 is equal to 3, because of course 7 to the power of 3 is equal to 343. Well, maybe I shouldn't say of course, like not everyone's going to see that, but you know, you get the idea. All right, this one, however, this is like a real beefcake. We actually need to use our log stuff on here because I can't even tell you off the top of my head what on earth's going to go on here, because this is like saying 3.7 to the power of something equals 9.2. Yeah, good luck with that. It's going to be like 2 something maybe. I have no idea. Let's find out. So again, using this identity makes this a real quick thing. We can just say it's log of 9.2 divided by log of 3.7. Let me toss this in my calculator. Log of 9.2 divided by log of 3.7 is going to equal, and I'll just round to the nearest hundredth. That's just usually good standard practice. It's 1.70. It would have to round up to 70. So there you go, 1.70. That's what that logarithm expression is equal to. Now this next one I threw in on purpose because there's a coefficient on front. Don't freak out about that. Solve your log piece first and then multiply by your coefficient, okay? And the reason you got to do your log first is, think of it this way. From bedmass, you got to do your brackets first. Well, we don't have any brackets, but then you got to do your exponents. Now, logarithms are inherently connected to exponents. So in terms of bedmass, in terms of your order of operations, your logarithm should come along with your exponents, right? So in other words, that's happening in that same step, hence why we're doing this first. Anyway, so log base 3 of 19, I'm going to ignore the 5 for now. Log base 3 of 19, we can just say this is going to equal 5 times log of 19 divided by log of 3. Oop, there you go, log of 3. You don't need that other little bracket down there. I'll do this all in one step, so I'm literally going to write it in my calculator just as I wrote it down there. 5 times, and then in brackets, log 19 divided by log of 3. And to the nearest hundredth, this gives me 13.40. So there you go. That would be how you would evaluate that. And I think we're good to go. All right, so next ones. This is going to lead into the next thing we're going to talk about here, but it's generally the same idea from before. Evaluate the following logarithms, and do you notice anything? If you want to give these a try on your own, you are more than welcome to. You can just pause the video here, but I'll go over them now. So anyway, so let's give this a try. For this first one, log base 3 of 27. What's kind of funny about this one is this is saying 3 to the power of something equals 27. Well, you can actually solve this using the old-fashioned way if you want, or you can solve it in your calculator using log 27 divided by log 3. It's up to you entirely, but I know log base 3 of 27 is actually equal to 3, so I'm just going to write that. Now, same with this one here, log base 3 of 81. Well, that means 3 to the power of something is equal to 81. I happen to know that 3 to the power of 4 is equal to 81. So in other words, this whole expression here, log base 3 of 81 is equal to 4. So this just means this is 3 plus 4, and that's pretty simple. That's just 7, right? Cool. Now this next one is a little bit more intense. This one I am going to have to use a calculator on, but notice we're using those same numbers. We're just multiplying them inside the log. That's kind of interesting. Anyway, I'm going to take care of that first because it's in the brackets here. We should really solve that piece first. So log base 3 of 27 times 81, which is 2,187. Yeah, good luck with that. 3 to the power something. It's 2,187. I wouldn't be able to tell you that off the top of my head, so I am going to use my calculator on this one. It's log of 2,187 divided by log of 3. And you are going to be amazed at what the answer is here. Again, I don't know why I'm plugging this in my calculator because I already know. But when you throw this in your calculator, you're going to see that the answer to that is 7. It's the exact same thing. Log base 3 of 27 plus log base 3 of 81 is the exact same thing as log base 3 of 27 times 81 all inside. This is not the same thing as saying log base 3 times log base, or log base 327 times log base 3 of 81. The 27 and 81 are actually inside the logarithm together. It's not separate logarithms being multiplied, because of course log base 3 of 27 times log base 3 of 81 would be 3 times 4, so that would be 12, right? This is something different. Interesting how this works. Now, I want to kind of really quickly remind you before I move on, when we're multiplying something together, it produces the same thing as when you separate them and add them together. Is that familiar to us from anything? What are logarithms connected to? Scratch your head on this one, and now I'll spoil it. Here it is, laws of logarithms. The laws of logarithms are a set of identities that are useful for simplifying or rewriting a logarithmic expression. There's 3 main ones. The one we did earlier about changing the base is technically one of them. It's just like the last one, and we don't really consider it a log law, at least I don't. But there's a first one that says log base b of m times n is equal to, if you separated those two pieces, as log base bm plus log base b of n. That's the one we just used, just in reverse. We started with this, and then we looked at the same thing as this, okay? Now the other one is log base b of m divided by n is, as you probably could guess, log base b of m minus log base b of n. So if you were to take this log and split it into 2 logs, you'd be subtracting them when you're dividing inside the logarithm itself, or vice versa, right? As for this one's really weird. Log base b of m to the power of n is equal to n times log base b of m. We're going to use this one a little bit later on in this chapter. But the way I always remember it is, it's like, okay, so if you got like a power inside of a logarithm, just take that exponent and take it to the outside, right? Like that one to me, it's a hard one to explain, but it's an easy one to execute, right? So you just bring that exponent out. Now, just so you know, these are essentially just extensions of the exponent laws you originally learned back in Math 9. That's what I was kind of alluding to in the last slide. The exponent laws, of course, said if you multiply 2 powers with the same base, you add the exponents. Remember, a logarithm will just spit out what the exponent is, right? B to the power of something of, is equal to m, right? So in other words, this right here just represents what that exponent was, okay? So when you multiply 2 powers of the same base, you add the exponents. When you divide 2 powers of the same base, you subtract the exponents. And then when you take the power of a power, you just multiply the exponents. So you're multiplying the exponent here times the exponent here, which is the log base bm. That one, again, is a little harder to see. I think the other ones are a little bit more clear in how they connect with the exponent laws. Now, just so you know, of course, the laws of logarithms are also in your formula sheet. Of course, we'd give those to you, and you're going to be using them quite a bit. So make sure you know where to access them. All right, moving on. So write the following as a single logarithm. We've got log base 3 of 9 plus log base 3 of 18. It wants us to write this as a single logarithm. We got to use one of our laws of logarithms here. When you're adding 2 different logarithms with the same base, you can just multiply these together. So this is like saying log base 3 of 9 times 18. And let's actually get a real number on that one. So 9 times 18 is 162. So log base 3, 162 is the exact same thing. So sometimes in certain situations, maybe it's nicer just to have it as a single log. And certainly, I guess if you were to throw this in your calculator, I can guarantee you'd rather go log 162 divided by log 3 rather than doing log 9 divided by log 3 plus log 18 divided by log 3. It would be a lot more work that way. Anyway, now the next one, 5 log base 2 of 3. This is going to be that weird power one just in reverse. Remember, if you had a power inside your logarithm, you can just take that exponent and bring it out to the front. Well, to go in reverse, we just go backwards, right? So in other words, this coefficient out in front can be tacked on to an exponent of inside the logarithm here. So this is going to equal log base 2 of 3 to the power of 5. And again, let's get an actual number in that rather than just some weird power. 3 to the power of 5 is equal to 243. So this is log base 2 of 243. Just using the laws of logarithms there, right? So we're just using those identities and throwing them through. Anyway, moving on. Right is a single logarithm. We got a whole like stitched thing here. Generally speaking, and again, you can tackle this in different ways, but generally speaking, I use the exponent one first. So if I have a coefficient out in front, I like bringing that into the logarithm first before I do anything else, right? It just makes my life a lot easier. So I'm going to bring all of these coefficients into each of their respective logs. So in other words, this 3 is going to be tacked onto the 4. That's going to give me log base 2 of 4 to the power of 3 minus log base 2 of 8 to the power of 2 plus log base 2 of 2 to the power of 7. Now the next thing I'm going to do is I think it's probably for the best if we actually get some actual numbers in these. So log base 2, 4 to the power of 3, I'm pretty sure that's 64. Yeah, it is 64. Log base 2 of 64 minus log base 2 of 8 squared, that I know is 64, plus log base 2 of 2 to the power of 7. Let me just double check that one. It's 128. 128, and there we go. All right, so now we can start using our other laws of logarithms. Again, it's better just to go from left to right on this one because addition and subtraction in BEDMAS are the same steps, so you should just follow them through left to right. So with these two, of course, we're subtracting two different logs. To write that as a single log, we'd have to divide the two things inside of it. So this becomes log base 2 of 64 divided by 64, which hopefully you know what that is, plus that log base 2, 128. 64 divided by 64, come on guys, obviously it's just 1, because 64 divided by 64 is 1. Write that out again. I'm really doing like a lot of writing this out here, but that's okay. Last but not least, of course, when you're adding two logarithms with the same base, you multiply the stuff inside. So in other words, this just becomes log base 2 of 1 times 128. I don't think I need to write that out. Hopefully you know 1 times 128 is 128. It doesn't want us to solve this, so we get to leave it right here. That is how we write that as a single logarithm. So this entire expression up here is the same thing as this piece right here. They're the exact same thing, which makes our life a lot easier in the long run. Anyway, moving on. All right, it wants us to evaluate these ones too. Evaluate, not even just write as a single log. This one is like actually evaluate, so solve what this is going to be equal to. Well, to evaluate this, you could honestly just plug it in like what we did like at the beginning of today, where you just use that rule to change the base into something more useful. You could do that, or you could write it as a single logarithm, because then it's a lot less things to punch into your calculator. I guess whatever floats your boat. I didn't say one thing or another on this one, but I will follow that through. Remember, my first thing I do is I bring the coefficients out and bring them inside. So this is like saying log base 2 of 16 to the power of 1/2 minus log base 2 of 8 to the power of 1/3. Now, hopefully you remember when you have a fraction as an exponent, that's like taking a radical, right? So a 1/2 exponent is like taking a square root. A 1/3 exponent is like taking a cube root. The square root of 16 is 4, so I know this is log base 2 of 4 minus log base 2 of the cube root of 8, which I know is 2. And since we're now subtracting these, we can write it as a single logarithm by saying it's log base 2 of 4 divided by 2. 4 divided by 2, you know, I'll write it out just so we can all see. 4 divided by 2, this is going to give us log base 2 of 2. Now, log base 2 of 2, if you really need to use your calculator, go for it, but it's really just saying 2 to the power of something, what this whole thing's equal to, is equal to 2. Well, that something, of course, is just going to equal 1. So if we just evaluated that one, it is equal to 1. Now, again, if you wanted to throw that all in your calculator all in one go, all the power to you. You can go do that. That's on you, whatever you want to do. All right, next one here. Log base 3 of 27 to the power of 4 divided by 81 to the power of 3. Holy smokes. You know, if you were to see something like this, you go, okay, well then this just clearly means I gotta like toss this whole junky mess right into my calculator. And again, by all means you can. But I'm a pragmatic person. I want to be able to do this without even touching my calculator here. I want to flex on people on this one. So on this one, if you were to ask me what's 27 to the power of 4 divided by 81 to the power of 3, I would tell you like I have no clue, leave me alone. So instead, we need to break this one down. It's kind of going backwards. Instead of writing it as a single log, this time it's better to break it down because then I have it in smaller little pieces that might be easier for me to chew on. So I'm going to break this down and split this, this fraction part into two different logs. This is going to be log base 3 of 27 to the power of 4. Put that in its own little brackets there. Minus log base 3 of 81 to the power of 3. I'm going to break this down even further, and believe me, it's going to really help me in the long run. I'm going to remove these exponents and bring them out front. Now, again, there's not really a definite rhyme or reason as to when we would break it down and when we would stitch them together. It just more or less depends on how comfortable you are with dealing with different situations. In this earlier example, I could have solved it initially as well, but again, getting it as a single logarithm actually made it easier. In this one, breaking it down is going to make it way easier. Anyway, moving on. So this will be 4 times log base 3 of 27 minus 3 times log base 3 of 81. Now let me look at just the log pieces here. Log base 3 of 27 means 3 to the power of something equals 27. Well, I actually happen to know that 3 to the power of 3 equals 27, so this just becomes 4 times 3 minus 3 times log base 3 of 81 means 3 to the power of something equals 81. Well, that something would be 4. So this is 4 to the power, or 4 times 3 minus 3 times 4. Or in other words, 12 minus 12, or even more disappointing, 0. Right? So log base 3 of this whole chunk is just equal to 0. Again, because it said just evaluate, you could have thrown that in your calculator all in one step and gotten 0. That's fine. But notice how I didn't even have to touch a calculator for any of this, because it was able to break down into more manageable pieces. Moving on. All right, so this one, bit of like a challenge-ish question, but once you break it down, you're going to see this one's actually baby food. If log base a of b is equal to 4.5 and log base a of c is equal to 3.7, then determine log base a of b over c. I'd like you guys to think about this one and give it a try on your own. So I'd appreciate if you just pause the video here and try it. And hopefully we're able to get a solution to this, but if you weren't, I don't blame you. This one is weird because I didn't tell you what the base is, and I didn't tell you what you're putting in each of these logs. So it's not like you could solve each of these independently because you don't have enough information to do that. But what it's saying is it's just saying determine log base a of b divided by c. Well, if you took this is like saying, all right, log base a of b over c is like saying log base a of b minus log base a of c. But here's what we know. Log base a of b is 4.5 minus log base a of c is 3.7. Told you it was kind of baby food. Once you see the trick to it, it's really not a big deal. 4.5 minus 3.7 is, let's just double check, 4.5 minus 3.7. Yeah, that's what I thought, 0.8. That's all that one is, just 0.8. Okay, so the hardest part about this one is identifying the fact that you can still use an identity even if you don't know any of the pieces that are in there. We don't know what a, b, or c are equal to. It doesn't matter though, because we know what log base a of b is equal to. We know what this whole piece is, so if we could isolate that one piece, we can just substitute in what we know it's worth. And same with log base a of c. Wasn't a big deal. All right, moving on. Next one, write as a single logarithm. This is another challenge one. I'd love to see you guys do this one on your own, so please pause the video here and give it a try. And now I'll go over it. So here we go. Again, golden rule here is get rid of your coefficients. So this guy's got to go, and this guy's got to go. So bring them in. This becomes log base b plus log, or sorry, not log base b, log of b plus log of d minus log e to the power of 5 minus log a to the power of 2 plus log a to the power of 1/2. You could write that as square root a as well, whatever floats your boat. Now, since it's just adding and subtracting logs together, just run through this from left to right. I'll do it one step at a time. If you're feeling really bold, you could actually try doing it all at once. I'm not there yet. I don't really want to do that, so I'll just do it one step at a time here. So if we're adding these two together, they do have the same base, we can just multiply them. So this becomes log bd minus log e5 minus log a squared plus log a 1/2. Now we got to get this guy in here. Remember, when you subtract, you need to divide. So this becomes log bd over e to the power of 5 minus log a squared plus log a 1/2. All right, let's bring this minus log a squared in. Again, we got to divide. When you divide this, really you're just dividing a squared, so times by 1 over a squared. So it's really going to go on the bottom is what I'm trying to say here is log BD over E5A squared plus, plus log A to the power of 1/2. All right, here we go. So now we got to like multiply these in. Watch what happens here. This is where it's going to get a little trickier. This is going to become log B D A to the power of 1/2 divided by E5A squared. This is all well and good as an answer, but it's not a fully simplified one. Like we have written it as a single log now, so that's good for us. But because there's an A on the top and there's an A on the bottom, we should really deal with this. Remember, when you are dividing powers, you need to subtract the exponent. So this is like saying A to the power of 1/2 minus, 1/2 minus 2. That's what it's really saying. So 1/2 minus 2 is like negative 1.5, or in other words, negative 3 over 2. What it means to have a negative exponent is you can just make it a positive exponent and put it on the bottom. Long story short, and again, you can test this if you're really wondering, your answer is going to be log BD over E5, and then A is on the bottom with an exponent of 3 over 2. Or if you prefer, the exponent on the A on the bottom could be 1.5, whatever floats your boat. There we go. We're done that one. All right, we got one more question here. Here it is. Well, two more questions. My mistake, but they should hopefully go pretty quick. It's a bit of a challenge question. If log base 2 of 3 is equal to x, then write an expression in terms of x for the following. You can try to give this one a try on your own. It is weird. It's kind of not a very satisfying question to finish, but you can try it on your own. And regardless of whether you tried it on your own or not, I'm going to go over it. So here's what it is. We want to write an expression in terms of x for these. We know log base 2 of 3 is equal to x, but we're asked to solve log base 2 of 12. Well, here's the thing. Using our our laws of logarithms, we've got to figure out how we can get like a log base 2 of 3 into this. Well, I could think of this as being log base 2 of, instead of 12, I could think of that as 3 times 4. Since we're multiplying two things together inside of a logarithm, we can split this up by saying it's log base 2 of 3 plus log base 2 of 4. Kind of a dumb trick to go with this, but it's just how it works. Now, log base 2 of 3 we know is equal to x, so we can write that as x plus log base 2 of 4 means 2 to the power of something equals 4. Well, 2 to the power of 2 equals 4, so we know that that piece is just equal to 2. So our expression is just x plus 2. Log base 2 of 12 is equal to x plus 2 for whatever x is. And again, you can use a calculator to solve for x, but that's not what we're doing. We're writing an expression in terms of x. That's all we're doing here. All right, same idea with this next one. Log base 2 of 81 divided by 16. I don't think 81 divides by 16. Let me try. No, yeah, it doesn't divide by 16, so we can't exactly do that right off the bat. But here's a few things I guess we can do. I know that 81 is actually a power of 3. 3 to the power of 4 is 81. So here's what I'll do first, just to try it. This will be log base 2 of 3 to the power of 4 over 16. Now I guess what I could do is I could split this into a subtraction. I can say this is log base 2 of 3 to the power of 4 minus log base 2 of 16. Now the other thing I can do here is I can take the 4 out by writing it as 4 times log base 2 of 3 minus log base 2 of 16. Now log base 2 of 3 is our x, so we've just isolated that. We got 4x now minus log base 2 of 16. Well, this is 2 to the power of something equals 16. Well, 2 to the power of 4 is 16, so we can say that's minus 4. And there you are. There's your expression for the other one. So I kind of told you it was kind of weird, but there may be some questions you'll encounter that are like this. Don't ask me why, it's just something we do. But anyway, that's how you go about doing it. Anyway, apologize, it was a bit of a long lesson, not too bad, right about 29 minutes. But page 400, questions 2, 3, 6, 7, ABC, 8, and 10. I'd like you to do those questions. Please make sure you're getting practice on this. A lot of the stuff that was in this lesson, it might have been looking pretty easy if you were just watching me do it. But believe me, there's more mental math that goes with this than you'd expect. So please make sure you're getting these questions done. And as always, ask me questions if you are stuck. I really appreciate when you guys reach out, and I'm always willing to answer. Anyway, best of luck.